stuff. It's the stuff I really like. But what we've found is that what you can do up here on the higher levels of this pyramid are really dependent upon how you parse and enrich the security log records coming in at the lower level. And this is true, outside of the security use case too. Your analytics and your machine learning are only going to be as good as the quality of data that you ingest. And by quality of data, we mean data that is parsed into fields, and so that we can do interesting stuff with searching and aggregation, and data that is enriched with information so that each document has a lot of interesting information in it. When we have those things, we can do very interesting stuff on the higher end with our analytics and our unsupervised machine learning and anomaly detection. Conversely, if the data is all over the place, it's harder to extract useful information out of that stuff. And I'll get off my soapbox now. So here, particularly today, what we're going to talk about, and the way this presentation is going to work, is that I'm going to do a few slides here on the high level idea and the architecture, and then Murali, who's smarter than me and has actually implemented this stuff in a more detailed way, is going to do sort of a deep dive into how we actually implemented this particular use case in Logstash, and we're going to have some code examples and things like that. And then after we've done that, we'll move back out and I'll talk about some of the other use cases we're working on now, because this event enrichment, everything builds on each other. We've previously given a talk on enriching events with the internal network information from your network, which is really useful, so you can tell where your different events are all coming from, which network segments, and maybe a little bit of information on the sorts of resources in those segments, which helps with making with contextual awareness. This is here we're going to talk today about tagging events coming in that from known indicators of compromise. So the our second acronym in this acronym salad day is IOC, indicator of compromise. That is a general term that means some sort of indicator to say that this particular account or device or process has been compromised and is a potentially performing malicious activity. It can be IP addresses, host names. We're going to focus on IP addresses today, but it can also be file hashes, email addresses. All those sorts of things are indicators of compromise. Those are the things we don't want to see in our network. And if we do see them, we really do want to know about them. So the next acronym, MISP, is an open source aggregator. It's a threat sharing platform, and it's the most popular one. It's got 6,000 contributors from all across industry and government. It's got many, many threat feeds that it aggregates and deduplicates and puts up on its server. And then you can go download whichever one of those you like. And you can also contribute your information back to it. The way it works, as we'll see, is that there's a public service that you can call to get the threat feeds, but you can also stand up your own internal MISP server. And the reason for doing that is because you can then start to incorporate your own internal threat intelligence. If you've had a known machine that's been compromised, or a known account that's been compromised, or you've seen activity that isn't publicly available, you can share that back with MISP, but you can also incorporate it on your local MISP server. And that gives you better, more specific contextual awareness. So we're going to use MISP today. There are other sources of threat intelligence out there. Some you can pay for, like from Anomaly. Others are available from government agencies. Many are specific to the vertical you're in. MISP, we're using MISP here because it's commonly used and commonly understood, but in a complex security environment, you might aggregate threat feeds from many different sources, including some proprietary ones that other people don't have. All of that can be aggregated into this MISP framework if you have your own server. What we're going to try and do with this MISP server is we're going to try and tag the incoming events based on if any of them have an IP address that we've known to be malicious. So we're going to find the list of currently known malicious IP addresses. These are IPs used for beaconing, any IPs that have been known to be associated with malicious activity. We're going to create alerts around them, watchers. We're going to retroactively apply some threat intelligence to older events, because a lot of times it's interesting to know if a newly identified IP address as malicious has been on your network for a while. When we get this threat intelligence into MISP, it doesn't mean that it was just that the threat actor has only been around that day. They might well have been around earlier. So we're going to talk about retroactively applying that information. We're going to show about how we can report on that threat activity, and we have some easy visualizations in Kibana to show that threat activity. The last thing here is the main part of the approach, which is sort of the Elastic way. Elastic is a denormalized database, which is why it is so fast and how it derives its great power. And what that means is that we like to store as much information on the individual documents, we'll call them events or documents interchangeably here, as possible. So we don't do joins with a lot of foreign keys. We don't do any of that. What we do is we try and, when we ingest the event, that's when we apply our threat intelligence to it. And if it is a known malicious, if it has an IOC that we know about, we're going to tag that event with whatever information we know about that IOC. And that event for as long as it's around, which, will be a while in your log storage, it will always be tagged with that information. And that allows for the really fast search that we've all come to love with Elastic. And so this is a denormalized approach to this stuff. Okay, so we're talking here about a high volume. This particular use case was, very high volume. It doesn't have to be. But we were 11. Actually, I think we had a few more than that. But we're running a whole bunch of Logstash instances where, in this particular case, we were getting our events from Kafka, and we were feeding 4 really large Elastic clusters with up to 150,000 events per second, 1 petabyte. So the point here is that in a high volume environment, and they all wind up high volume eventually, you have to carefully choose what you do in terms of event enrichment so you don't slow anything down. Because in a high volume environment, your challenge is to ingest these events without any delays. Now, if we're using Kafka, delay is not the end of the world, because Kafka will buffer the information, and then when things clear up, it'll come through, and there's going to be spikes in event flow. And we talk about that in some of our other presentations. But in general, we want our events into Elastic as quickly as possible without any delays. And we don't want Logstash to be a choke point. So our implementation here has to take that into consideration right from the very beginning. And that's the point of this slide. So because we design this from the ground up, there are various ways. Logstash is a wonderfully flexible platform, and there are many ways to enrich events. So we looked at a few and ruled some out, and this is what we found. Memcache, not really optimized for an IP search. It doesn't survive a reboot, as the title indicates. CDR is another Logstash filter plugin, which a filter plugin is used for event enrichment in Logstash. This is not really an option because it can only return a Boolean, and we want information on the particular malicious IP, like, when was it detected? What does it do? More interesting is an HTTP filter, which could call MISP for every event coming in and say, hey, do you know whether or not this is a bad IP? The problem with that is, while it will certainly work, it's going to be slow because it's going to be an awful lot of HTTP calls. We can also, from within Logstash, we can call Elasticsearch and enrich events that way. So we could read an Elasticsearch index, and if we were to store our malicious IOCs in there, we could enrich our events on the way in based on the information in that index. The problem is that it doesn't really scale the Elasticsearch plugin. We need to be actually faster than that because it's 150,000 events per second. So those things we ruled out based on our own experimentation, and we we came down to these last three. So MaxMind, which is the subject of a previous presentation of ours, we really like. MaxMind is what Elastic uses for its GeoIP enrichment. So MaxMind contains a really optimized database that's keyed by IP and or by IP range, and it's great for looking up a particular IP and retrieving information about it. And we figured out how to use that MaxMind not just for the geographical information about that IP, but we can also store anything else we like about it. So it is what we use for our internal IPAM information. But in our particular use case, we're only talking about 800 to 1,000 unique IOCs that we're looking for because we didn't want any false positives, and we'll describe that a little later on. So we were selective in our feeds, right? It's not of much value, this thing, if you're flagging every event as potentially malicious. Our use case was, if we flag an event as malicious, we want to know that it's malicious. We don't want any false positives at all. So in that case, at any one time, there might be 800 or 1,000 known bad IPs out there in the MISP database. And for that, we don't really need to use this really optimized MaxMind plugin, and we don't need to build our MaxMind database because there's only 800 or 1,000 entries. So we thought that a more lightweight solution and easier for everyone to understand and easier to implement was a translate filter. And that is extremely simple. And all it does is it reads a CSV file and it looks up an alpha key in that file. And if it's there, it retrieves the information, in the subsequent columns. This works really well, we found, for up to about 80,000 entries. So given we've got 1,000 unique entries here, we've got plenty of room to grow in terms of more IOCs. So we found that the translate filter was a great solution for this particular use case in Logstash, and we'll show you what that filter looks like a little later on. We also found a great feature in Logstash called the HTTP poller. And what that does is it can poll a URL periodically and create a CSV file. So we also, and this is out of band from the ingestion, as we'll see in a minute. So we're ingesting events in Logstash. They're coming in at this extremely fast rate. We're enriching them based on the CSV file. And then out of band, Logstash is also once in a while going out to MISP and recreating that CSV file so it's always got fresh information in it. If a new IOC comes out, we want to know about it pretty quick. So these are the two filters we're using, the translate and the HTTP poller, and that's what we're going to be talking about the next few minutes. So my last slide here is our general architecture. So if we start at the top here, we've got a log record. And the log record has, in red under the IP address, that's it's an actual malicious IP, a current malicious IP in MISP. And this log record seems to originate from that. It might be a proxy record, like somebody's trying to go out somewhere. It might be somebody pinging you. It might be somebody on your network, like trying to log in and getting shut down. It could be anything like that. Or it could be beaconing out from a device that you have that's been compromised. It's trying to go out and call home and ask the command and control what to do. So this log record is going to be ingested by Logstash, as we said, via Kafka. And it's going to go through a translate filter. And the translate filter is going to read a CSV, a comma delimited file of IOCs, and it's going to enrich them. If an IP address from this log record matches something in there, we're going to grab that information. We're going to flag that record as enriched, and we're going to put it in the event index. So that's the main flow, the log record to the translate filter and into the event index, now with the enriched information. Pretty straightforward. Now, how are we going to build this CSV? Out of band, Logstash is going to run this HTTP poller every hour or so, or every half hour, and it's going to go talk to a local MISP server to get the latest IOCs. And that's what it's going to use to recreate the CSV. And as long as we're recreating the CSV, we also write our latest IOCs into a different index that we have in Elasticsearch, because we can use that stuff later on for all kinds of things. So this is an out-of-band process. It doesn't affect the speed of ingestion. It's creating these CSVs, but it's not having any real impact on the ingestion of the records, because we've got a lot of them coming in and we don't want any problems there. In terms of getting the EOCs, the IOCs, we have an HTTP polar. It is going to talk to a local MISP server, which we stood up on site. And then that MISP server, also out of band from everything, every hour or so, goes out to the main MISP service and downloads the latest threat feeds. So our local MISP server is, always up to date on its threat feeds. That's where it would get this bad IP address, that 45155205225. It's going to put that it's going to put that on the local MISP server. The HTTP polar is going to get it, write it to the CSV, write it to the IOC index, and then as the records come through, if any of them have that IP on it, they're going to get tagged as such, and then we can write all kinds of beautiful visualizations around that and alerting and all that sort of thing. All righty, so that is the architecture. I'm going to stop sharing and let Murali take it over from here. And then I'll come back at the end. He's going to talk about how we implemented this architecture.
Thanks, George. Okay, yeah, here is how we implemented here at the client's place. So we did, there are different ways of pulling your MISP feed for enriching your data. But what we decided to do was to build a local MISP server where we can download feeds from multiple feeds that are available from the MISP site, and also stored locally to enrich events as the log records goes through this process, or the CSV file, as George mentioned using in his previous slide. So what we did was we set up a small VM with 2 cores and 4 gig of RAM, and there is a RPM install available at here is the URL, and the installation steps are very simple, and it took just about an hour or 2 for us to bring up the MISP, also to enable the feeds and schedule the jobs to run every hour to pull the events from the MISP feed, MISP available feeds that we have on that site. So we basically built this VM. We got the VM installed or built for us. Then we installed the MISP using the instructions available on this GitHub URL. Give me a second, okay. Sorry. So we installed the modules that are needed, and we also opened some firewall ports as per the instructions. And then we also enabled SSL so that it's not using the default port 80 to retrieve those events. So that's how we built the MISP server. And then the next slide is, so here are the feeds that are available, the default feeds. There are about 61 of them. So, and to enable those feeds and cache them locally, it's very simple to do that. So basically there's an option called list feeds, and then you go and select the feeds that you want, and then you can basically enable the selected and also enable caching for selected, so that's those feed is locally cached on the MISP server. So that's very simple. So the next, do let us know if you have any questions on these slides. We will try and answer the question.
Yeah, I'm keeping an eye open for them, Rally. So.
Okay. So in our use case, we initially looked at three of them. There are out of the 61 that's available. We just looked at three feeds. One of them, the alien vault. The other one is the IP sum aggregation of all feeds with no false positives, and IP sum aggregation of all feeds level 8 with no false positives. There are feeds available with different attributes like SHA-256, domain. Uh, there are tons of feeds available with different attributes. So in our case, we just selected these three in our use case. And then the next slide is, and we also enable these feeds to run every hour. And this basically, there's a, under administration, you have an option to schedule the tasks to run, how frequently you want the data to, the pull or the feed to be populated or refreshed. So we decided to go with 1 hour, and we selected those three fields that we enabled in our previous screen or slide. So we have the data refreshed and available cached locally on our MISP server. Now comes the interesting part of how do you make the CSV file available for all the Logstash servers, so that as the events go through Logstash, it can be those CSV, that information can be looked up locally on the server, on the Logstash server, not on the MISP server, but also enrich them as it goes through each log source. That's what you're going to see in the next coming slides. So we, as George mentioned, we use the HTTP poller to basically poll events using a REST search API, and it also has an option of pulling what the attributes that you want. In our case, it was just IP address. It could be as IP source, or it could be IP destination, or it could be IP source colon comma port combination. IP address and port combination. That's basically what it is. It could be either a source address or a destination address, or like a source domain or a destination domain. Those are the available attributes. So that's the HTTP poller we used, and also we wanted to make sure that the data is not duplicated in the CSV file as well as in the index. So we used translate filter to look up the CSV file to see if it exists. If it existed in the CSV file. If it did, then we basically didn't do anything with it. And if it didn't, we basically added to the CSV file. So let me, instead of just sharing, going through the slide, I will show basically the sample configuration we used in our Logstash. So here is, let me know if the screen size, if the code or the Logstash configuration is visible. I will, if not, I can increase the font.
It looks okay to me, Murali, for what it's worth.
Okay. Okay, thanks. So here is the URL that we are pulling the MISP feed from, and we are using a REST search API. And then we pass the credential, and we also pass the what type of content type, and accept basically the coding we are using. And then the the return format we need, we wanted a CSV file, and then the attributes that we are looking for. In this case, it's the destination port, a destination address, destination port, source address, and source port. And then we want the data to be pulled for the last 1 hour. And then we basically said it should run every 30 minutes. That's basically what the HTTP poller does. We defined in our input configuration, input section of our Logstash configuration. Then we use the CSV filter to basically define the column headings. Also, we defined some default, added some fields which is available in the CSV filter, like the lookup type and priority for those events. This is what we thought we will assign the priority as, but it could be different for different use cases. And then we removed some fields which we didn't want to store in Elasticsearch Index as well as in the CSV file. And then so based on the attributes that we retrieved, we basically created a key that we basically we would use that in the next section of the code to look up in the CSV file to see if it exists. So we looked at the IP destination port and the source port first, and then we did the similar thing for destination port, destination address and port combination, and source address and source port port combination. And then and we used a Ruby script to basically look up to see if that file, if the key existed in the CSV file, and if it didn't, then it would basically return a flag, which in case if it didn't exist in the CSV file, it will return a flag called add, and if it did exist, then it will not return it will return a different flag or attribute for this field. So if it's not add, then it generates a document ID, which is basically like a whatever key that you're trying to add. Whatever key you're trying to add, it basically removes the dot. Like for example, if it's an IP address, it removes the dot so that it's a unique document in Elasticsearch. Because if you go with the Elasticsearch own document ID, there is a possibility that an IP address may exist twice. So this logic made us prevented duplicate entries being indexed into Elasticsearch Index. And then this is where the CSV file gets updated with a key and a value, which we defined above in here. Key is the address and port, and the value is whatever attribute additional information that comes with the IOC, with the IP address, or with any attribute. For example, if it's a charter 56, then what other attributes that comes, additional information comes, that will be part of the value key value pair. That's how we stored the CSV file locally on the server, on each of the Logstash server. So this is basically a small Logstash, like a Logstash configuration that runs with 1 gig of RAM and 1 pipeline worker. It doesn't need much processing at all, much other resources to process that MISP feed. And that's one. The next slide is to how we use this information in Logstash to enrichment. So let me go through that, and then I'll go back to the slide. So the idea is the same. So if a document has an IP address, it could be a source address or it could be a destination address. Since our use case is based on an address, so we basically use a translate filter to look up the key that you're, in this case, translate filter to look up the IP address in the CSV file. And if it exists, then it will return the value which is associated with the key. And if it doesn't, then the fallback is it's a normal address, IP address. So this is what we do afterward to enrich the event. So basically we say if it's not normal, then we add the additional attributes that's available for that given IP address. And then we basically add a field called IP destination port. This is just a field that we defined. That this could be anything. This basically we define the category, what category it is, and what IP address or port combination it is, and then we define the priority and event ID. This is all part of the key which is available in the CSV file. And also we stored the reported date when it was reported as malicious. So we enrich the event with this information and add it to an Elasticsearch index, the source index which we are trying to ingest into Elasticsearch. And sorry. So this is the translate filter that I showed you guys. It's process each IP address as it comes through, looks up the CSV, looks up the IP address in the CSV file, and if it exists, then it adds the other attributes like the category, the comment, and the date of reported date and severity. That's basically what it does. And if it doesn't, if it's a normal IP address, then it doesn't do anything with that IP address. It just goes and looks for the next one. That's enriching incoming events. And this is the CSV file that with the malicious IP addresses that we downloaded. The MISP or the log/stash configuration that we showed earlier basically generates this CSV file. And this is a malicious IP address that existed in this CSV file. And this is how the event shows up as part of the log record. I hope this is visible. So this is the date, and this is basically what the category is, network activity, and this is the IP address and the priority and what the event ID is and what reported date is. So initially it was the reported date was in a POE format, but later on we converted this to show it as like a real human date. This number doesn't mean anything to me, so we've basically fixed that. And the malicious, what the MISP type is, if it is a source address, then it will show as malicious IP source. And if it's a target or destination, then it will show as malicious IP target. And similarly, if you were to look for malicious domains, then the IP will change to malicious domain source and malicious domain target. That's basically how it will show. And accordingly, the header, which in this case the IP test port description, that will change to domain description. Depending upon what attribute we are trying to pull, this information will change accordingly. So that's that. And so we also set up like a watcher. The reason for the watcher is to make sure that this information is available historically. Like, for example, if we have retention of like 60 days with your data, So this, we didn't want the information to be lost. We want this information to be available like for 365 days or for 2 years. So we basically created a watcher that basically looked for those fields that we enriched with, and if it did, then we basically created an alert index which stored that information for historical purposes. In this case, we extracted only certain fields, but if a client, if based on the user requirements, we could add multiple fields. This is just an example for malicious IP, but we could also use the same logic or apply the same logic for other attributes too, like domains or SHA-256 or any attribute that you have that you're trying to enrich the data with. We can do this. And this is how the dashboard looks like. The top shows all the unique IP addresses that showed up in the data in our log source, and it gives you a count of how many times that IP address showed up. Like for example, IP showed up 140 times, malicious IP, and here this one shows like malicious what this basically shows the IP address trying to access internal domains, internal domains or internal whatever targeted assets, internal assets. And similarly, if an internal IP address trying to access malicious domains, then this is the dashboard that shows that. So basically, this says, okay, this IP tried to access this domain, and vice versa. It's like it's a heat map that shows up how many times this IP address tried to access this domain, and in this case, is the other way around, how many times an internal IP address accessed the malicious domain.
Yeah, and I'll just say that we had to redact a little piece of it. That's because this is real data. So
Right.
Some of those, the internal domains are redacted.
Yes.
Can you enlarge this a little bit, Mirali?
Yeah, sure.
Oh. Oops. Here we go back. That's my slide.
Yeah.
So one is sort of inbound attacks and the other is outbound beaconing kind of stuff.
Right. So the top layer shows the IP address and the number of times. Like for example, this IP address, one of them showed up on the 18th, had 140 times it tried to access an internal domain.
Mm-hmm. And these are the feeds we chose for MISP. I mean, you can choose whichever feed you like, but as I said, the ones we chose, the particular ones are known to be 100% true positive. So, this doesn't look like, I mean, actually, this doesn't look so bad. I mean, when you think about 150,000 events per second,
You're right.
It's not an outrageous amount of threat activity, but all of it's real.
Right. And so, for example, this malicious IP tried to access these domains, internal domains, and this basically gives you. So, if in real time, if I were to look at this visualization, if I move my mouse over this green bar, it'll show how many times it tried to access. It gives you that information. Similarly, here, it'll say, okay, this IP address tried to access this domain this many times.
Alrighty, and there's many more
and
stuff you can do.
Okay. I'll stop
Okay.
sharing my screen.
All right.
Thank you.
Thank you. That's great. So let me get to where I have to go. Let me just go to page 2. I should have been doing this myself. So what we're going to talk about here is the little ways ways in which we can, possibilities for combining and enhancing this solution. It's basically stuff we're working on. So in our previous presentation, as I said, we used the logstash maxmind filter to do a very similar sort of thing to indicate the network segment of particular internal network resources, because as we know, like all network resources are not created equal, and some are like way more sensitive. Like say all this data is totally made up, by the way. This GDPR segment in France might be like really sensitive. And if you see malicious addresses messing around in there, you might want to prioritize that a little bit more. If you see beaconing from the PCI segment, that's a bad thing. But if you see, some beaconing from, the mailroom, maybe that's not as important. So this is using this type of event enrichment here, which we can combine those two things together and prioritize the malicious activity and show sort of summary metrics of malicious activity across different network segments, which is super useful, I think. So there's that, and from that you can create visualizations. This is a sort of a fake one, but you could visualize the network traffic, and we could visualize the malicious network traffic. It's particularly useful for, say, trying to figure out lateral movement and things like that. And this is all hunt team stuff that people who are searching for threats on the network or resolving, like they've seen malicious activity and alerts been fired. They're now responsible for researching it. They're the security analysts or the response team. This is where the internal network information can really come in handy. So now this is some of the other stuff we'd like to do. Like for us, the issue of event enrichment is part of the larger issue of contextual awareness. We want to make our machine learning jobs and our alerts and our correlations and our SOAR systems to orchestrate stuff and our human beings as empowered as possible as they respond to these threats. That's the general idea. So, we've talked point solutions up to this point, but there's many things we can do with, or anyone can do, of course, with event enrichment to add contextual information to events. And I think this is a really powerful thing, and it's very difficult to do outside of Elastic, really. It's the nature of the Elastic database makes this stuff really easy. And as I said, we've done this in extreme, this works in extremely high volume environments with this sort of event enrichment for the using the maxmind for IPAM, using the translate filter for domains and IPs. We've done this, at very high EPSs, and it works. It's performant. And so we don't see any reason to stop with just what we've done so far. One thing that we'd really like to do is to create some device contextual awareness. So we could harvest, what we're trying to do is harvest some vulnerabilities from Qualys or Red Seal or any vulnerability scanner, Nessus. And then because that'll be a big database, we'll index that by IPs in the maxmind database. And then as the events come in, we can indicate right on the event itself what known vulnerabilities exist on this device. So if this particular Unix box has a known default password, and it shows up with people SSHing into it from a known bad IP, that's kind of useful information, right? I mean, that's actionable intelligence. It's contextual awareness. That's really important. And so that's things we're working on. As I said, SOC managers like that sort of thing. Another thing that's super interesting, and this list is by no means exhaustive, is the machine state, machines are in a different state all the time. And I guess vulnerability is a state as well, but also the historical state of what's happening. A lot of times viruses get cleaned up from particular endpoints, and it might have gone to the wrong spot and got 10 viruses on it, and you've cleaned up 4 of them, or 5 of them, or 8 of them, and you think you're fine. But it's useful information to know that that particular endpoint had a virus infection, because when you see it beaconing next week, you'll know where the problem was. You'll be able to determine root cause. And so what we'd like to do is to maintain machine state, and that would be very easy to do with the MaxMind database as well, or possibly with the translate filter, depending on which one to use, depends on your volume. But this is a great thing to be able to know the machine state, or possibly the user state, what's happened in the past on this machine. Having that contextual awareness available immediately, both to your automated jobs and also to your humans that are reasoning these decisions as to how to handle this, how to triage it, who to call, how serious is this event, what's the next step. The more information you can put in front of them right away, as part of the, right on the event itself that they're investigating, the less work they have to do, the quicker they're going to have the response, and the more accurate the response is going to be, because it's going to be contextually aware. This is true of humans and machine processes. Lastly, not lastly, but, dear to my mind is the idea of identity in general. This forms a basis for some really cool UEBA type solutions, the simplest of which is identity attribution. We could maintain session state pretty easily with an approach that combines the enrichment that we're talking about here. We could detect user logons and user logoffs. We could update a MaxMind database, and we could know when a user logged onto a machine and when they logged off to a machine, and that could be maintained in an Elastic database, and we could enrich events with that information. And it would also be very useful if people are actually, the incident response team is trying to figure things out. We could also create a translate filter, if it's not too big, of sensitive users. Like, not all users, just like some machines are in very sensitive network segments, some users are extremely sensitive users, and others don't have that much privilege to begin with. The ones that are really sensitive, it's good to know about that right away. If you see malicious activity for an event that that's flagged as malicious activity, and it has a really high power user associated with it, then the danger exists that that user account, or that service account, which is what we've seen a lot of lately, has been compromised. And that is all hands on deck kind of situation, because that's going to create more accounts, and it's just going to create more and more problems until you fix it. So it's really good, rather than having your machine, your automated processes, or your human beings having to go into the identity system and say, like, what kind of account is this? What can it do? What groups is it in? What's its role? That sort of thing. If you have that information on the actual event, and there's no reason why we can't do that in an efficient and performant way, that's going to make all your machine learning and your security orchestration and your humans just that much more powerful. So these are just some of the use cases that I think that are in our future, and in future presentations by us, or maybe by you. I think that this is an exciting world, and I think that there's not many products that can do this right now. So here's a little more information. If you're interested in, I know we talked a lot about IPAM and MaxMind and GeoIP. We've got a presentation on that if you're a glutton for punishment. And then here are all the sites for the, just various sites in the presentation. I'm sure we can go see this. The MISP project is a good one, and the GitHub for the Logstash plugins is super useful. We found these things, especially this GeoIP and the HTTP polar and the translate filters. These 3 are really useful. If anyone's interested in, like, this, MaxMind allows you to look up a huge database of IPs really fast, and that just has many applications across all kinds of stuff. And if you create your own MaxMind database, you can put any information keyed by IP in there and use that. So that's really interesting. So I am done now, but I'll leave this up. If anyone has any questions, Murali, you want to read them out? Do you see the questions there?
No questions so far.
All right, well, let's wait here a second and see if anyone
Sure.
wants to have any questions, just throw something into the chat and we'll do our best. I know there was one question that came up earlier, which was interesting, which was, Murali, why do we write the IOCs to an elastic index in addition to the CSV? My answer was that it was so that we could retroactively apply the threat intelligence to older events that perhaps occurred before it was a known integrative compromise, but I might have that wrong. Why
No,
do you write?
you're right. You're absolutely right. That's the reason for that index to be stored
Yeah.
in Elasticsearch as well.
And I don't think we showed any of that functionality in this demo, but if you're interested in it, you should, just feel free to contact us anytime on this. We're happy to share the code that we've put together here, and we're happy to talk about use cases and what we did and what works and what doesn't work. It looks like we got a neat chat. Do I dare put it right on the screen? Oh, let's just do it. Live dangerously, huh? Oh, I can't see it anyway. Let's see.
So,
All right, so here we go. Yes.
Go ahead.
By retroactively, no, what we're doing is we're providing the hunt team a way to, we're not going to create a new index in the existing records. The question was, when I say apply threat intelligence retroactively to older events, David asked, do you mean that we're going to create a new index from the existing records now that we know that they're malicious? And I don't know the answer to that. I think it was mainly for hunt team functionality, but there's no reason why you couldn't do that using watchers. What do you think, Alec?
So the idea there was like, so suppose if a malicious IP showed up as one showed up in the recent report, and if they want to go back and take a look to see if that existed. So basically what we did was we created visualization, which will look up the MISP index as well as the source index, and it will basically create like a dashboard similar to what we showed earlier. Like, let me share my screen for a second and see if I can explain that way. So the idea was to have the ability for an analyst or whoever is here, as George mentioned, the hunt team, to look up that IP address across in the MISP index as well as the source document over a period of time. Like they want to know in the last 90 days, did this IP show up? So they had the ability of going back in time to look for those. No, we are not creating an index. It's just like a visualization that showed up similar information as to what you see here. So if it's an IP, then it will say, okay, this IP tried to access these internal assets. And if it's a domain, then it will, if it's an internal IP, then it will say, okay, these are the domains that it tried to access. That kind of, that's what we meant by retroactively applied the threat intelligence to older data or already processed data.